SwayamPrabha. Digital India. Educated India.
Good afternoon, everyone. Today we will discuss some important aspects of flow modeling. Such aspects can be compared with the grammar of a language. If you want to enjoy creation of a given language, poems, verses, you have to know grammar in order to understand nuances of that language. Similarly, if you want to model flows and heat transfer problems with greater competence, you require to understand some aspects of flow modeling, and we will discuss those aspects today. Before entering into the domain of actual flow modeling, I have already mentioned about it. So we will learn this, and here we'll take up a model equation. We'll apply all our concepts, all our ideas on those model equation, and we will see its character, we'll see the result. Now, this model equation is called Burger's equation. James Burger, very well-known fluid dynamicist, developed this equation. It's called one-dimensional Burger's equation. It has all the components of full-fledged Navier-Stokes equations. Like this has, you can see, we have written the equation where u is the velocity and nu is the coefficient of diffusivity or viscosity in case of modeling fluid flow problems, and zeta is the property that can be convected and diffused, and this is the temporal term. Now, if the right hand side is neglected, then the equation will behave as a simple analog of Euler's equation, which will have temporal term and the advective term. So, some cases will include the diffusion, some cases will only study the advection. Now let us consider general vorticity transport equation. This is temporal derivative of vorticity equal to, I have taken the convective term to the right hand side, so minus sign has come. This is v dot nabla, which will give in Cartesian coordinate I del u del x plus j del u del y plus k del z dot product of I into e plus j into v plus k into w. So that means this operator is u del u del x, v del u del y, w u del del x, v del del y, w del del z. And it can be operated on velocity, temperature, or vorticity. So this is basically the convective term plus nu grad square omega, which is diffusive term. I have written lambda is differential operator, v is the velocity field, and omega is vorticity. If we integrate it over a fixed region in space given by capital R, this is maybe a volume, a fixed region described by a volume through which fluid is coming and going through. Now we can see this is the we are then integrating the whole equation over this space variable R, and we can get simply this equation. Here we will go term by term. Del omega del t integrated over space R. This, since if we define a space and we are not changing the space with time, so this time derivative can be taken outside. Del del t of omega over the space R, it is integrated. Similarly, this convective term v dot nabla omega dr integrated over R, this can be written as nabla dot or grad dot v omega into dr, which is again can be written as area integral v omega dot n dA. A naught is the area which is encompassing the volume of interest. Now this is a subtle mathematical expression. Certain operations have gone in, like grad, if it is operated over v and omega, we can write v dot grad omega plus omega into divergence of v. Simply expand grad dot v omega. Now if we expand this way, for incompressible flows, this part divergence of v is 0. So we can drop this. So that means we get this as v dot grad omega. Now v dot grad omega, it is integrated over space over volume. If this volume integral is converted into area integral, then we can write area encompassing that is A naught. So v omega dot n is the unit normal vector dA. So in this operation, Gauss divergence, this Gauss divergence theorem has been applied, and A naught is the boundary of R, n is the unit normal vector, and dA is the differential element of A naught. Now, so two terms, temporal term and the advective term, we have handled. Temporal term we have seen can be written as del del t of integral over R omega dr, and this second term can be written as minus integral over area describing the space, V into omega dot NDA. And the remaining term is the viscous term, which is nu grad square omega integrated over R dr. This we can write as nu into grad omega dot NDA over the space. How? This is also this quantity nu into integral of grad omega over the area A naught is basically can be written as volume integral, again applying Gauss divergence theorem, nu into again integral over the volume divergence of or grad dot grad of omega dr. And then this grad dot grad, if those are operated, we will get grad square omega dr integral over r. So integral over r grad square omega dr is basically nu into, it comes from nu into area integral of grad omega dot NDA. So all three terms now we have at our disposal. We can write the integration of vorticity transport equation as del del t integral over r omega dr equal to minus integral over the area that is describing r v into omega dot NDA and nu again integral over area grad omega dot NDA. Now this way, when we can write, we can say that time rate of accumulation of omega in R is equal to net advective flux rate of omega across the area that is describing the region R plus net diffusive flux rate of omega again across R, that is across area that is describing R. The concept of conservative property is to remain this integral relation in the finite difference formulation. That means when the formulation will be done, we will be able to appreciate that convective fluxes are through formulation crossing the entire space smoothly and diffusive flux also crossing the entire definition of space smoothly. Now, how typically that can be shown or proved? We will take a recourse to again Burger's equation. This is conservative form of Burger equation. As we said that now we are saying conservative form. That means this convective term, this original form has to be convoluted to a conservative form. And how that is done? That is done in this way: del omega del t equal to del del x of u omega. And then if we discretize using FTCS, forward time central space, we can write omega at ith point n plus 1 minus omega at ith point n divided by delta t equal to, so we are writing expressing this using central difference centered in space, ui plus 1 omega I plus 1 minus ui minus 1 omega I minus 1, all are at nth level. And let us consider a region which is R, one-dimensional volume, running from, and we are dividing it by number of compartments, running from I equal to I1 to I equal to I2. This is I running through. So now we evaluate this integral, which in discretized form, if we write, it is 1 by delta t, then summation of, since we are integrating over this, summation of omega delta x over I equal to 1 to I equal to. So left hand side becomes this. Then right hand side simply will become summation of this entire space. So summation of this quantity delta x over I equal to 1 to I equal to 2. And exactly we are doing that. 1 by delta t omega I n plus 1 delta x minus omega I n delta x, I equal to I1 to I2, I equal to I1 to I2. This is equal to what we did here. Basically, this quantity will be integrated over the space. I equal to 1 to I equal to 2, and I have done a small mistake. Delta x will come here. Delta x has come on the left hand side. Delta x will appear on the right hand side too. So this will be basically now then half, again another mistake, equal to will come in front of this. So it is half I equal to 1 to I equal to 2 u omega I minus 1 n minus u omega I plus 1 n. This minus sign has been absorbed inside, and then we can write this way. So please, be careful. I have done two small mistakes here. I should have written a delta x here, and then as a result of this interoperation, this quantity summation over I equal to I minus I1 to I2 delta x is equal to this half summation of I equal to I1 to I2 u omega I minus 1 minus u omega I plus 1 at nth level. So it will run over this control volume, this quantity from I minus 1 to will get it up to I plus 1. So left hand side we are not changing. Right hand side, that means this flux says if we now vary I, if we write I equal to I1, then it is I1 minus 1, and this will produce I1. Next term will be, basically we can write I equal to 2. So then it will be I1 minus 1 to I1 plus 1, that means I1. So I1 plus 2I2 will run. So next term will be I1 plus 1. So I1 plus 1, if we substitute here, that will be I1, and then this will be minus quantity I2 I1 plus 2 at nth level. So we will be able to form an array. Just substitute I equal to first I1, then I equal to I1 plus 1, I equal to I1 plus 2, I equal to I1 plus 3. Ultimately, I equal to I2 minus 1, I equal to I2, we write. And then if you do that, simply express these two terms by substituting I equal to first I1, then I equal to I1 plus 1, then I equal to I1 plus 2. And this way, if you go up to I equal to I2 minus 1, I equal to I2, you will get, array of these two quantities, and you will see always, one term will get cancelled with the another term in the next expression, and all the terms will be this way. Intermediate terms will be cancelled out, and the final expression which we will get will be basically, so I have given dot dot dot, so finally I equal to I2, and then this is small I equal to I2, so I2, and this is I2 plus 1. So then you will see that we'll be able to write u omega I1 minus half minus u omega I2 plus half. So again, let me repeat that we will write I equal to I1 to I2. I will vary here, and then first term will be I1 minus 1 I1, second term will be again I1 plus 1 will come here, so it will be I1 plus 1, then I1 plus 2 will substitute small I1 plus 2 will come here. So we'll get the expressions, and the expressions can be arranged in such a way that all intermediate terms will get cancelled, and finally we will be able to write from here u omega I1 minus half at nth level minus u omega I2 plus half at nth level. So basically these two last terms, this is the last term, this will constitute this, and this is the first term, this will constitute this. Basically u omega we have written at I1 and I1 minus 1, average of that, that means whatever is entering through this dotted line, and finally u omega at I2 and u omega at I2 plus 1, so by 2, and this is basically whatever is crossing through this dotted line, we will get that. So whatever is entering, that is going out. So equation 5 states that the rate of accumulation of omega I in R is identically equal to the net advective flux rate across the boundary of R, running from I equal to I1 to small I equal to I2. Thus, the FD analog, finite difference analog, to implicit part of integral equation 3, Burger's equation, has preserved the conservative property. So you can see, if this way we write, all intermediate fluxes will get cancelled, and whatever is coming in, that will be going out. Final expression will be this. So by formulation, we are preserving the conservative property. But non-conservative form, if we write minus u del omega del x, then and then integrate it, we will differentiate it first. We will get omega I at n plus 1 omega I at n divided by delta t equal to minus u at nth level. Here omega I plus 1 minus omega I minus 1 centered in space at nth level divided by twice delta x. And again we will run I equal to I1 to I2. Then if we write down the expressions of this integral, here also we have to write delta x here. I have missed that, please be careful. I will try to represent these two slides in my next lecture again so that you can correct that. So, and then you express in this way. But in this way, now if you substitute I equal to I1, then I equal to I1 plus 1, I equal to I1 plus 2 up to I2, you will see you form the array taking 2-3 terms. That means I equal to 1, I equal to 1 plus I equal to I1, I equal to I1 plus 1, I equal to I1 plus 2. And then last 3 terms, maybe I equal to I2 minus 1, I equal to I2. You will see all intermediate terms are, not cancelling at all. So basically fluxes are by definition not eventually balanced. So while performing the summation of the right hand side of you have written equation 7, it can be observed that terms corresponding to inner cell fluxes do not cancel out. Consequently, an expression in terms of fluxes at inlet and outlet section, as it was found earlier, could not be obtained. Hence, finite difference analog of 7 has failed to preserve the integral Gauss divergence property, that is, conservative property of the continuum. So again, little repetition. This is conservative formulation, and conservative formulation final expression of left hand side is equal to this. I said that I have missed equal to sign in front of this expression. Here if you keep on substituting I equal to I1, then I1 plus 1, I1 plus 2, maybe 3 terms, and then I equal to I2 minus 1, I equal to I2 plus 2 or 3 terms. You will see fluxes can be arranged such a way that all intermediate fluxes will get cancelled. In the domain, the inlet flux will just go out as outflux. Influx will just go out as outflux. So basically, it will, by formulation itself or by writing itself in this way, conservative form, we are retaining conservative property, whereas by writing this way, which is equation 6, we are not retaining conservative property, non-conservative form. So from here, that means the calling equation 3 as conservative is now, again a small mistake, is now clearly understood. However, the conservative form of advective part is of prime importance for modeling fluid flow and is often referred to as weak conservative form. So instead of writing del u del t plus u del u del x plus v del u del y plus w del u del z equal to 1 by rho del p del x plus nu grad square u, we can write it in this way: del x of u square, del y of uv, del z of uw. Similarly, y momentum equation, our non-conservative form is del v del t plus u del v del x plus v del y plus W del V del Z. Instead of that, we will write del V del T plus del X of UV del Y of V square and del Z of UW. Right hand side we are not touching. So all the advective terms, the convective terms can be written in conservative form. Now if we only write the advective terms or advection in conservative form, then that is called weak conservation. In a similar manner, if we try to write all the terms as first order derivative of the x, y and z and t, then we will be able to get something which is called strong conservative form. You have seen that what we have done now right hand side also enters into the expression in terms of wherever it fits in del xy or del x or del y or del z. You can see del u del t plus del x of u square plus p by rho minus nu del u del x. If you move it to the right hand side, it will be del x 1 by rho minus 1 by rho del p del x. That has been brought here. And if you again shift this to right hand side, this will be nu del 2u del x2. That has come here. So similarly, del u of uv and right hand side from Laplacian u, if you bring del 2u del y2 on this side, you will be able to get this. And if you bring nu del 2u del z2 on left side, you will get left hand side, you will get this. Similar way, v momentum equation or y momentum equation can be written, or the z momentum equation can be written. When we write in this way, it is called conservative form. Strong conservative form. Strong conservative form is not a mandatory requirement. Because of ease of formulation, at times strong conservative form is preferred. In quite a few well-known algorithms, the equations are discretized in strong conservative form. This way in strong conservative form. But as I mentioned earlier, weak conservative form, that means writing convective derivatives or advection terms in conservative form, is often very, very helpful. And in almost all the well-known algorithms, it is done this way. So we have learned first, conservative form of convective term. It always balances convective flux through its definition. Second is, this conservative form of equation can be again written in two different ways: weak conservative form and strong conservative form. Now again I will go back to Burger's equation in terms of zeta. So del zeta del t plus u del zeta del x. And now we will write two different finite difference schemes. One is, you can very well appreciate equation 1 forward in time, and a non-conservative form also forward in space, not centered in space but forward in space. Second one, again forward in time, zeta n plus I at ith location n plus 1 minus zeta at ith location n divided by delta t plus u zeta I plus 1 at n minus zeta I minus 1 at n divided by twice delta x. Now this is called again non-conservative form central difference. Now if you apply von Neumann stability analysis, which we learned earlier, that formulation is stable or not from numerical stability point of view, although we do not have viscous term here, but if we try to perform von Neumann stability analysis, we will find both these formulation 1 and 2 are unconditionally unstable. That means whatever you do, it will blow off. The calculation will not converge. So obviously, we have to look for the reason and look for the remedy. I have given name of few scientists. One is Gentry, Martin, and Daly. Again, this group is from Los Alamos, and Ranchal and Wolfstein. Again, both of them were at that time at Imperial College. Although Ranchal is an Indian, many of you might be knowing him. He was at Imperial College. Wolfstein, he is from Israel basically. Very well known, two students of Professor Spalding, and they are these three are co-workers of Professor Harlow at Los Alamos. Anyway, to cut the long story short, that they experimented in those days. People were trying to evolve Navier-Stokes solver and several other experiments with full Navier-Stokes equations. So these were very relevant and very important. Now they found out that the very efficient way to get such derivatives stabilized is the following, and that is we have written equation 1 can be made stable by substituting the forward space difference by a backward phase difference scheme, provided the carrier velocity is positive. That means if u is positive, and then instead of forward difference scheme, if we write backward difference scheme or rearward difference scheme, this will be stable. If u is negative, then if u is a negative velocity, then this is okay. Then forward difference scheme must be used to assure stability. For full Burger's equation, the formulation of the diffusion term remains unchanged and only the convective terms will matter. So what we will do, we will formulate, we have seen earlier, we will only consider convective term, number 1, and number 2, we have already learned, we have already sort of tested that conservative form is more effective or more useful. So we will apply this philosophy. That means if u is positive, go by rearward difference, backward difference. If u is negative, go by forward difference of the dependent flow variable. Now we have exactly done that. Zeta I n plus 1 minus zeta I at nth level by delta t equal to minus zeta I n u zeta I n conservative form u zeta I minus 1 n plus viscous term for u greater than 0 and minus zeta I plus 1 minus u zeta I for u less than 0. That means for u negative, and this is I minus 1 for u positive, zeta I plus 1 minus zeta I minus 1 for u negative. And since conservative formulation, u and zeta are together. It is also well known that upwind method of discretization is very much necessary in convection dominated flows. It is basically what is meant is high speed flows, and I will discuss later that this was a major bottleneck for solving full Navier-Stokes equations for higher Reynolds number, and this was specifically a problem with finite element formulation. Anyway, we'll not confuse with those information now. What we'll do that we will take it up equation 3 and equation 4 and we'll test its effect on again a one-dimensional domain running from I minus 2, I minus 1, I plus 1, I plus 2. And once we'll take u as positive, so in the positive direction, another occasion we'll take u as negative, u running in the negative direction. That means in the opposite direction of the coordinate system. So consider again model Burger equation as I said. So and only we will consider temporal term and the convective term. Del zeta del t equal to minus del x of u zeta. And if we go for FTCS, so u and zeta, u I am not writing specifically I plus 1. It is understood that u is with zeta. Whatever is the zeta's coordinate, u is with it. So zeta I plus 1 minus u I zeta I minus 1 by twice delta x. This is, we know, forward time central space. Otherwise, consistent good formulation. So we have rewritten that because we will very soon do the analysis on this template, on these equations, on this equation with these terms. Consider a perturbation epsilon m equal to delta in zeta. A perturbation will spread in all directions due to diffusion. This is a very nice concept and very natural concept. If you take a, for example, steel plate and place a small heated object at the center of it, you will see slowly, entire plate in all direction equally it will be heated up, temperature will increase. Or if you throw a stone in a still water in a small pond so that you can observe, you will see ripples are going with the same speed on all directions, and this is very natural way of describing diffusion. So diffusion will be, if we give a perturbation, diffusion will propagate on all directions. So since we have taken in an inviscid model, so the perturbation, the going on all direction, that part is eliminated, as if it is not diffusing. So we have switched off the diffusion term, and perturbation to be carried along only in the, so then only in the direction of velocity it will go. So it is like coloring a spot in a flow stream. So if flow stream is not very gently going in one direction, that color will keep spreading in other direction. So for u greater than 0 and this epsilon m equal to delta, perturbation at mth space location, all other epsilons are 0. Now if we substitute here, having perturbed it at mth location, I equal to m, we are trying to see what happens when I at the next time step at I equal to m plus 1. So here we'll simply substitute I by m plus 1. So this will be zeta m plus 1 at n plus 1th level minus zeta m plus 1 at nth level by delta t equal to minus u into, then m, if we substitute I by m plus 1, it is zeta m plus 2. So nothing is there with if we perturb at mth level at, not the next point but next to next point, and also at I minus 1, that means m minus 1, if we substitute here, that means at mth point. Mth point we have disturbed. Delta is there at mth point. So we can see this is plus, is becoming twice delta by u delta by twice delta x, which is acceptable, right? Because at the next point you will feel at m plus 1th point in the space, you will get some effect of perturbation, giving perturbation at mth point. That is why we have written which is acceptable. However, at the point of perturbation, what is happening? If we substitute I by m, here also if we substitute, so this will be zeta m at n plus 1 minus zeta m at n divided by delta t equal to, here I is substituted by m, so at m plus 1 and m minus 1. Now perturbation is not there at m minus 1 or m plus 1. Here at mth point, earlier case, perturbation, we substituted by perturbation. But here at m plus 1th point, no perturbation. M minus 1th point, no perturbation, 0. Which is not very reasonable, because after giving perturbation, the next time step itself, you are not able to feel anything there, no quantity there, is not very reasonable. Again, I've retained the same form of equation at m minus 1th point. So again, I is substituted by m minus 1, and this is u zeta, and this u zeta, I should be substituted by m minus 1. So m minus 1 means this is m, and m minus 1 means this is m minus 2. So at m minus 2 point, nothing is there. At, if we give m minus 1, this is mth point. So mth point, delta perturbation. So we can see this is becoming equal to minus u delta by twice x, which indicates that at m, but finally we are observing at m minus 1th level. m minus 1th point, sorry, at the point m minus 1, spatial point. Now u velocity is in the positive direction, so I plus 1, I plus 2, all are points in the positive direction. U velocity is moving in the positive direction. After giving a perturbation, if we get effect of that perturbation in the I minus, at I minus 1 point or at I minus 2 point, which are in fluid mechanical language upstream points. So when U is positive, upstream point should not get perturbed, but we can see upstream point is getting perturbed. So this is not really acceptable. We can say transportive property is violated. Now, but it was FTCS formulation, right? Equation 6 is FTCS formulation. So again, we will conservative form of equation, that means equation 5 will go for basically we'll go for the formulation for U positive. Now what we said, if U is positive, then it will be backward difference. So for positive U, we have to involve a point which is at the behind, which is basically upstream point. So U zeta in minus U zeta I minus 1n by delta x for U greater than 0. So for positive U, we involve the upstream point or the backward difference. So then we can write this form. That means we know now that U is positive, so the difference is I minus U zeta I minus U zeta I minus 1. Again, we are perturbing at mth location, and then we will see what is happening to m plus 1. So we substitute I by m plus 1, and this is at m plus 1. We did not give any perturbation at m plus 1, so we will write 0, perturbation value is 0. But if m plus 1 is substituted to this I, this is m, perturbation value was given there. So this quantity is at the next time level, at the next point, is becoming U delta by delta x, which follows the rationale for the transportive property. That means in the forward point, it must move. At point M of the disturbance, again in this equation, you substitute all i's by m's. So we have done that. Now since at mth point disturbance was given, but m minus 1 point there was no disturbance, so we can see at mth point at the next time level what is happening. Some effect of perturbation we are able to see. That means the perturbation is being transported out. It has a negative sign also. Again, if we observe at n minus 1th station, we have repeatedly written this equation so that we can easily substitute m minus 1, and if it is m minus 1, there is no perturbation at m minus 1. If we substitute I by m minus 1, then it is U zeta m minus 2, there is no perturbation there, so these are 0, equal to 0. So at the upstream point, that means the point behind, there is no effect. So this signifies that no perturbation effect is carried upstream. In other words, upwind method, maintains unidirectional flow information. In conclusion, it can be said that while space center difference are more accurate, space center difference schemes, they are more accurate than upwind differences, as indicated by Taylor series expansion that we have seen earlier in our first few lectures. The whole system is not more accurate if the criteria for accuracy includes transportive property. Because here there is a bias. The fluid velocity is inducing that bias on the space. So this is not a stagnant space. We are not solving heat conduction problem. Here the medium is moving and flow velocity is affecting. So the finite difference quotient will be very appropriate if this effect is inducted, if this effect is mimicked in formulation. And that is what is done if we do or introduce upwinding. Upwinding means, again, we'll go back by the definition given by Gentry, Martin and Daly and Ranchal and Wolfstein, that you go for first order difference quotient, especially del U, del X, del V, del X, such quantities. You discretize it using backward difference. That means using upstream point which is behind, if the flow velocity is positive. If the flow velocity is negative, then you involve downstream point. That means forward point. So go for forward differencing for the negative, locally negative velocity. Go for backward differencing for positive velocity. This philosophy is called upwinding, and we will see that when we will formulate a complete problem, this information or this guideline helps us a lot. Although things may not be so much straightforward, but the hidden idea will remain the same. Effectively, we will involve upstream points for positive velocity and downstream points for the negative velocity, which we'll see be very stable and also will be very accurate. But to maintain accuracy, we have to involve some additional technique, additional care. We'll do in the subsequent classes. We'll stop here today. Thank you very much. This was the conclusion that we will in transportive property is one directional flow property. Maintaining that, we have to go for upwinding. So we have progressed up to this. We will take up from here in the next class. Thank you very much.